I just hit the record button, and that's good. And now I'm going to share a screen with you just for a moment. And so I will go over here. I have to learn how to do this again. I will share my application screen, and I will go up with PowerPoint. And Linda, you should see PowerPoint, yes?
Not yet. I don't think you've started sharing your screen yet.
Okay, let me try it again. Okay, so, oh, I know what I needed to do. Thanks. Okay, and Linda's actually sharing something right now. Linda, let's just, I guess I can stop sharing and you can share, Linda. People are answering you, so that's fine.
Yeah, I don't need to share for them to do the poll.
Okay, great. Okay, so I will share in a bit, but we'll just see how this is going. And I do care, and Linda cares as well. And I am going to ask you to respond to this. This is totally anonymous, so no one knows, you know, what you were saying here about, you know, how things are. And I'm not really sure. I guess maybe we only have 10 people in attendance.
Yeah, and 2 of
Uh,
them are us, so there's only 1 no response.
okay, so I'm going to say, well, okay, so far so good. But I will tell you is that the person who's saying they're not well, and I hope that's not like a physical thing that they're not well. But anyway, if things aren't going the way you want them to in the course, you should be talking to me, and I can recommend many remedies, or talk to Linda, and she can recommend many remedies as well. So now I'm going to try that sharing the application screen again, and see if I can do a better job this time than I did the first time. And now, Linda, you should see a PowerPoint slide.
Yes, I do.
Good. Thank you, Linda. Okay, and Linda is a busy young woman, and so she often will not be at this class, but she'll be doing other things. But she did agree to stop in and do a little bit of a cameo at the beginning. She's always welcome to drop in, and anytime she can stay, that's a blessing. I did introduce Linda before. She is one of the best math students ever to study at the College of DuPage. She has a very impressive resume of accomplishments that she's done here. And she is within, and this may not make a lot of sense to you yet, but it will during the flow of this course. She is within epsilon of finishing her master's degree in math. So we're very blessed to have Linda involved in this. I've worked with Linda many times, and it's always been a blessing, and students really find a lot of value in what Linda has to provide. Linda not only is a strong math tutor and runs GSG sessions, but she also has a full-time job where she is the STEM coordinator, that's science, technology, engineering, and math, in the Learning Commons. So, you know, Linda's gainfully employed full-time, and she's doing this as a favor to, well, to me and to you. So we're very blessed to have Linda. Linda will be intimately involved with me throughout the course, and I'm just going to turn it over to her for her to say whatever she wants, and then we'll go from there. So Linda, the floor is yours for as long as you want.
All right, this shouldn't take too long. I am putting something in the chat real quick. This is the link for our guided study group that is going to be starting next week from 11 to 12 p.m. on Mondays and Wednesdays. So that'll be right after your guys' class ends. And then on Thursday, then I have another session that's going to stay remote throughout the entire semester for people who have a harder time making it to campus. And that'll be Thursdays from 5 to 6 p.m. I also want to share my screen real quick, so I'm going to steal the floor from you.
Do I have to stop sharing for you to do that, or?
You may need to. Nope, I'm good. Okay,
All right,
so
great.
if I go under just your typical collaborate screen, then you see when you log in, this is something like yours would look like. If you go under the student support tab, then this is where you can find a whole bunch of different drop-ins that the Learning Commons offers. So if you're looking for help with this course or any of your others that you may be enrolled in, then this is an awesome place to look. And we have our hours listed out here. But specifically for math drop-in, if you guys need a little bit of extra help outside of the guided study groups, then I'm also available on Mondays and Wednesdays from 5 to 7 p.m. And again, that'll be starting next week. If you do need help in person, then we are going back to campus on, I believe, the 7th. So we'll be available for in-person appointments then as well. All right, that's all I got.
Okay, well, I'm going to ask some questions, and then I'm going to give students an opportunity to ask you, questions if they have them. One question I would have, and by the way, sometimes as a teacher, I ask questions that I know the answers to. But anyway, this question. Okay, so Linda, there's a question that just came up. What the hell is GSG?
Yeah,
Now,
so GSG is guided study group.
I did try to explain this in some of the videos, but let's hear it from Linda. So go ahead, Linda.
So guided study groups basically mean I'm meeting with Professor Bradley for at least an hour a week, typically more just because we like to talk to each other, but we're in the same loop. So I'm aware of what's going on in class. He's aware of what's going on in the GSG meetings. And then I'm meeting with you guys, in this case, for 3 hours a week. So if you decide that you need help, then that's a perfect avenue for you to get it. It's not mandatory. You don't need to go. I'm not taking attendance or anything, but it is an awesome way for you to get assistance as needed.
And Linda does give me feedback from the GSGs, and I will ask her, hey, how many people came, or something like that. But she does not report to me that, oh, Susie came, or she wouldn't ever say anything like, here Patel is angry about something. Everything would be anonymous. Linda is a trusted advisor. She has your interests at heart.
I
And
just tell them that people are angry, not you in particular.
yeah, okay. So anyway, and that's good. And I do listen seriously to what Linda says. And often I do, whatever she recommends. And so that's that can be useful. That here I have a question, Linda, and then I also have a comment too. My question is, so do the students have to stay for the 2 hours or the hour if they show up?
Absolutely not. It's a come as you need basis. So you can show up in the middle of the hour, you can show up for 5 minutes. If you just want to pop in and say hi, that's totally fine too. It's really just whatever you guys need, then that's what you come for.
Okay, I'm going to make one other comment. And Linda, this is not in terms of it's a suggestion. Okay. I think when you sent out the information, and I'm guessing because I was looking and it looked to me like that's what you did. You sent it out as an email to the students. Is that correct?
I sent it out to everyone enrolled in the class, but yeah.
Yeah, okay, send it out as an email. Now, I don't know, these students may have their lives more together than me, but I know I spend a lot of time. Um, Linda, we'll come back and address that question, and I don't know if it was to you or me. I spend a lot of time saying, damn it, I got an email about that, but I don't know where the hell the email is. And IT is also really good about coming in and deleting emails and things like that. So one thing that I strive really to do is I strive when I communicate with y'all students is I strive to put it in an announcement, and I will be emailing that to you at the same time. But you see, if you lost the email and you say where it is, you can always go back because I don't delete those announcements. So those are there. So Linda, as you do those kind of things, that would be good to stick those in the announcement, at least if it's something that people are going to want to maybe refer back to, or they're not going to remember, or they're going to lose the email. Now, did that question totally get answered, Linda? And I know that you were doing some commenting there, but maybe just for the benefit of everybody, perhaps somebody who's not watching do we have, is there anything to say there about
Yeah,
the
so
question
someone
and
just
answer?
asked if it was always going to be online or if it was going to be in person once in person comes back on February 7th. And I was just letting them know that Monday and Wednesday will be in person since that's when the guided study group is scheduled right after the class. So I figure if you guys are already on campus, then that would be a good time for you to come in and get help. Thursdays will remain online since that's kind of a weirder hour, so more so for the people with full-time jobs and have a harder time making it into campus like that.
Okay, any other questions of Linda? Okay, I have one question. Linda, how is 7? Is she in attendance?
She's doing great. She's hanging out by the front door waiting to go outside.
Okay, well, you might have to go and care for that, but that is okay. So thank you, Linda, and you guys can reach out to Linda for all kinds of needs that you might have. Okay, I'm going to share my application screen with you, and we're then going to go back to the PowerPoint thing. And you all should be looking at a PowerPoint slide now. And so we had Linda's cameo. What we're going to do today is we're going to finish the prerequisite review. Then we're going to begin talking about limits. I am going to launch what I call low stakes assessment number 2 today. And your questions are always welcome, so you can ask those at any time. Okay, so that's what we have going on today. All right, now these were, and I don't know if I talked about this problem or not, but we're going to do 2 projectile motion problems. And at the end of these 2 problems, we will have finished our review. Okay. So I'm just going to read this problem to you, and then we're going to go through a solution, and you should be able to understand the solution and you should be able to do a problem like this. And this problem involves, a handful of things. Okay. And it involves some trig, I guess. So Jason Kendall throws a baseball with a horizontal component of velocity of 25 meters per second. It takes 3.00 seconds to come back to its original height. Calculate its horizontal range and its initial vertical component of velocity and its initial angle of projection. Now, one thing it doesn't tell us is how tall Jason is, and it also doesn't tell us at what height he releases the ball. And you might say, well, don't we have to know that? And the answer is we really don't, because the question says it takes 3 seconds to come back to its original height. So Jason is throwing this ball. You could think about him throwing it from a pitcher's mound or something like that. And so if he's throwing the ball, he's throwing it, he probably releases it and it goes a little bit up in the air and then it comes down. So it takes 3 seconds for it to come back to its original height, which actually is Jason's release point. Okay, now, what we, we've got that, and we're supposed to calculate its horizontal range. That means how far did it go before it came back to that original height? What was the initial vertical component of velocity? And what was the initial angle of projection? Okay, so let's talk a little bit about that. And I am thinking, and wow, I'm going to stop sharing just for a minute. I'm going to go back and share in just a bit, but I want to call on someone and I want to be careful who I call on. Let me look at just this, at who's here. Hey, Alex, would you mind being my go-to guy because Linda is taking care of her dog and doing other things? Would you be willing to be my go-to guy? And I'm pretty much just going to ask, hey, can you see this and stuff like that?
Yeah, absolutely.
Okay, so excellent. So I'm just going to be calling on Alex kind of repeatedly. I'm never going to be asking him a hard question, just as, can you see things? And he will give me some good answers. Okay, so now I'm going back then, Alex, and thank you for doing that. And Alex, now I am asking you a question. I am wiggling my cursor on the screen. Can you see my cursor being wiggled?
Not at the moment. No, I don't believe it's
I'm
sharing.
going to try. I'm going to try one other thing. First of all, you can see a PowerPoint slide, yes?
I
No.
do not. I think it just shows the regular icon that we all have in front of our
All
page.
right, so that's not what I want to do. You see, you're adding value to this class already. So I'm going back there. I'm going to be sharing my screen again with you. And now I'm doing it better probably and soon. Okay, so now you should see a PowerPoint slide, Alex.
Yes, it just came up.
All right, excellent. Now I'm wiggling my cursor. Can
Yep.
you see my cursor wiggle?
Yes, I can.
Great. Now that's good because that means I kind of will use this to point and so on and so forth. Okay, so all right, so let's just work this problem. Now, there are certain facts in physics that have to be part of this problem. And you might say, well, I didn't take physics or I don't remember all the physics. Well, that's kind of okay because I'll teach you all the physics that you need to know to do these problems. But this does also involve a little bit of physics. And by the way, during this course, I'm going to do something that physics students will like because I am going to derive later in this course the physics equations that you used in high school, and I'm going to show you how calculus says they must be true. But anyway, it takes 3.00 seconds to come back to its original height. So what happens is this Jason guy releases the ball, it goes up, but then it comes down. And this is a physics fact that we can prove, but it's a physics fact that the time up is the same thing as the time down. So if it takes 3 seconds to come back to its original height, that means it was going up for 1.5 seconds and it was coming down for the rest of the time. So one observation that I make here, and I just wrote this with a pencil, things like that. I say, well, it takes 1.5 seconds to reach its maximum height because it goes up, stops going up, and it starts coming down. And you all have thrown baseballs or softballs and stuff. You know that's the way balls work, and that's what happens. You may or may not have known that the time up is the same as the time down, but we'll see that as we discuss these things along. So anyway, I know it takes 1.5 seconds to reach the maximum height. Now so it was 3 up, 3 down, but half of it was going up and half of it was going down. Now, one question okay, and the horizontal component was 25 meters per second. So that means, and I'm wiggling my cursor down here, that means the ball is traveling 25 meters per second in the horizontal direction. Now, this is another physics fact that you may know, you may not know, but you kind of have to know a little bit about this to to understand this problem, and that is that the horizontal and vertical motions are independent one with another. And we're assuming that there is no air resistance. And so you see, he throws this ball with a horizontal component of 25 meters per second, but that didn't say anything about the vertical component at all yet. Okay. Um, but that does allow us to calculate its horizontal range because we know it reaches it comes back to its original height 3 seconds later. So distance equals rate times time. So the range is going to be distances rate times time or velocity times time. So the horizontal range is going to be 3, that is the time, times the velocity, which is 25 meters per second, is 75 meters. So the answer to its horizontal range is directly 75 meters, and you don't have to do anything very fancy to come up with that. Okay. Then it asks about its initial vertical component of its velocity? Well, you see the horizontal component, I've got a little right triangle that I'm kind of pointing at down here. So I have 25 is this part of the triangle, but then vertically going up, I have another part of a triangle. And what I want to find is the velocity and the angle. So I want to find the hypotenuse eventually. Actually, its initial vertical component, that's what I want to find. Okay, so I need to do a little bit of physics here, okay? So he throws a velocity, but then what happens is there's an acceleration, and the only acceleration is in the vertical direction, and it is the acceleration due to gravity, which I'm calling minus g here. And it's in the opposite direction of him throwing the ball up. And so the velocity at any time is equal to v0, that means the initial velocity in the y direction, minus the acceleration times the time. And this is equal to 0 when I am at my top of the trajectory. So this is something that's going to be true, and we're going to do this over and over again in this class. But v0y minus the acceleration times the time is equal to 0. That means the initial vertical component is going to be v0y minus g times t is equal to 0 at the top. And I've already figured out that at the top it's 1.5. So that means that v0y, I just put gt on the other side, and g, there's different things people call g, but in meters per second it's 9.8. And so this is 9.8, that's meters per second squared, times 1.5 seconds, and that gives me meters per second. And if I do those
Sir,
multiply, yes,
remind me, how did you get 9.8 again?
I didn't. Well, okay, and that's and thank you for asking questions. That's very good. Everybody should do that. Okay, it is known in physics classes that the acceleration of gravity is 9.8 meters per second squared. So that is kind of a given in this problem. And I pulled it out of my, I used to teach physics. I pulled it out of my physics knowledge. And that's something that you should know, but now I've told you that. And so as we talk,
So
this will become
9.8 is the what?
the
The standard what?
acceleration due to gravity.
So it's the standard gravity acceleration.
It is, yes, exactly. Well put,
Okay.
actually. Okay. And we will be talking about, some of these physics things and engineering things as we go along. But that's where it came from. And I didn't, bother to write that down, but you asked the question, so you were again helping us just like Alex is helping us. So thank you, whoever that was. Okay. All right, so that means that at the initial time, it was 14.7 meters per second. So that means the trajectory then, it's 25 going horizontally. It is 14.7, and let's see, did I round off or not? I think that's actually exact. But anyway, going up, it is 14.7. And again, horizontal is perpendicular to vertical. And so I now have the vector components going horizontally and vertically, and I've answered the second question. Its initial vertical component of velocity is this 14.7 meters per second. Now, the last question is something I really haven't talked about even in the videos yet, but it's another element of trig stuff that you should know about, and we are going to be studying inverse trig functions. So now I know I have a right triangle. I know it's a right triangle because horizontal is perpendicular to vertical, and I know the legs, so that means I could figure out the hypotenuse, except I could use the Pythagorean theorem, figure that out, but no one asked me to do that, so I'm not doing that right now. I'm just answering the question that was asked. But the question was, hey, what's this angle? So that's this little angle that I'm showing here as theta, okay? Now, from our right triangle trigonometry that we did review, we know that the tangent of theta is equal to the opposite over adjacent. That is 14.7 divided by 25. But then I also know that I can use my calculator and find the inverse tangent. And so if I actually did use a calculator for this, I'm good, but I don't do this calculation in my head. I actually knew it was about 30 degrees, but anyway, the arctan, or the inverse tangent, that's theta, and so that is what angle has a tangent that is 14.7 divided by 25. So you can plug that into your calculator, have your calculator set on degrees, so it doesn't come back with radians, and it tells me that was 30 degrees and change. Now I'm going to pause for a count of, I think what I'm going to do is stop sharing, just in case people are doing, I don't know, comments or something, and I'm going into comments. Okay, so the first, okay, there's a whole bunch of comments here. Okay. All right, so I'm going to answer them in the question that was here, and then when I'm finished answering any that I see here, um, then what I'm going to do is I'll accept any questions that people want to just go off mic and do. Okay, so first of all, someone said 9.8 is gravity, right? I would say it, and again, I'm being very precise, and I know, so I'm not correcting anybody. I'm just saying it's the acceleration due to gravity is 9.8, and that's a constant of nature on the Earth, and so that's one of the ones that you'll want to know. And we will do problems like that, but I'm working this problem, so I'm letting you know that. And then somebody else said, yeah, it is gravity. So they were answering the question. And then somebody says, sorry, can you tell me when the LSAs are due? Well, at the end of this period, we will have 2 LSAs out there. And one of them is going to be due on February the 7th or before. Okay. And somebody, okay, so, and the second LSA, and I haven't necessarily told you that, but that's going to be due on Valentine's Day, which is February the 14th. Now, somebody made a comment and said February the 4th, and maybe I screwed that up. Oh, so, then that got fixed. That's February the 7th. So that's all good. And I think I've dealt with all the comments that are there. Okay, so, and I'll say more about that LSA later, but I guess what I want to do, or maybe I'm asking you about, is, let's see, are any other questions? And I'm going to count to 5
Yeah.
in my head very slowly.
Hello.
Yes, go ahead. I hear you.
So for the LSAs, there's nothing in the LSA when you open it up. Is it gonna be like that all the time? Like, are we gonna get the actual problems in class and then like just do it at home, or like, are you gonna upload
Well, I'm
anything?
going to say, and by the way, I'm not trying to be rude with this. I
Yeah.
will, I will try to post them in the syllabus tab somewhere. And someone says it is in the syllabus tab, and maybe I've done that, maybe I haven't. Um, like Linda, I'm busy, and I know you guys are busy too. And I do what I can when I can, and things like that. But I did tell you what the LSAs were because they were in the presentations, and I will be posting them there. And so your question is fine. I'm going to be posting them there, but you're attending the class, and if you're taking notes or something, you'll be seeing those anyway. Yeah, I will be putting them there in plenty of time for you to do them.
Yeah. I just
I hope that
thank you.
answered your
Sorry about
question.
that.
Okay, great.
Yeah, yeah, I
And
got
again,
you.
that was a good question. Um, and if I ever am using my teacher's voice with you, that doesn't mean that I'm angry with you. It's just I have a teacher's voice. I once upon a time was trying to have a relationship with a woman. She was younger than me. This was after my wife had died for more than 10 years anyway. But I was trying to have a social life, and we went out to dinner, and my date for the evening told me, hey, cool the teacher's voice, because I was talking like that to her. So anyway, all right. I'm going to count to 5, and then we're going to move on. I'm going to be pretending there's no more questions about that problem that I just did. Okay, I hit 5. Your questions are always welcome, but now I'm going to go back because there was another one that we're going to do, which is slightly different. So, Alex, I'm going to be trying to share a screen again, and I'm sharing the application screen again. And Alex, I'm just going to say things you should be seeing, and if you're not seeing them, you can let me know. Okay, so Alex, we should be looking at a PowerPoint slide again, but now I'm advancing it, and now we're looking at a different problem, and so I'm getting an enormous amount of feedback, but I don't know.
Oh, that's probably me then. Sorry, I had my mic on because I was just going to say that it's up. So you are
Oh,
all.
well, and good, and thank you for that.
Yep. Yeah, everything looks good. Sorry about the feedback.
Okay, so yeah, um, I I love you guys and I love teaching. I hate teaching in this manner, but this is kind of what we have to do now, and so I'll do it. Okay, so anyway, here's a different problem. This is the last review problem we're doing. So a diver jumps off a pier at an angle of 25 degrees with the initial velocity of 3.2 meters per second. Now, the reason I chose to do this problem was there's different information being given here. In the last problem, we had to find out what the angle was. In this problem, we know what the angle is. And so this diver is jumping off the pier, and we're to assume the level of the water is the same as the pier. Now, this is not especially exciting pier, but what that means is, I'm wiggling my cursor here, that the level of water is right there at the lip of the pier. So, you know, you could have run off the pier and you'd be running into the water, I guess is what that's saying. You wouldn't be falling. But anyway, so this person jumps up, but they're jumping at an angle of 25 degrees, but the initial velocity is 3.2 meters per second. Now, this might not be obvious to y'all, but that is this vector that's going at an angle of 25 degrees. That's what this means. So I have to resolve this 3.2 meters per second. I have to resolve that into its horizontal and vertical components. And so this just means I can do a little bit of right triangle trigonometry. So you see this horizontal component of that velocity is going to be the hypotenuse times the cosine of the angle 25 degrees. So 3.2 times the cosine of 25 degrees. And again, I'm very good, but I do not have memorized cosine of 25 degrees. So I'm using my calculator for that, but I can do 3.2 times the cosine. And this little wiggly thing here means approximately equal to. So that's approximately equal to 2.9. So it's not totally equal to 2.9. It's approximately equal to 2.9. Okay. And the vertical component is going to be, you see, whatever this is divided by 3.2 is the sine of 25 degrees. That's the opposite over the hypotenuse. So this is, and that looks like 32. That really should be 3.2. That's, I fucked that up. So that is 3.2. Sorry about that. It is 3.2. Actually, I'm sorry about two things. I'm sorry I left it off, and I actually have a pretty good vocabulary. I don't have to use the F word. So anyway, what happens there is that's there's a point there that you can't see. It's invisible, although I did use it when I did the calculation, and you get that this is approximately 1.35. Okay, so that is that is good. So that is the initial velocity. Now, this is the equation I talked about before in the vertical plane. And so what I have here is the initial velocity minus the acceleration times the time. And the acceleration is gravity again. And you see it's 9.8. This time I used 9.81. Don't worry about that. I'll tell you what to use. But that's 9.81. But you see the initial velocity, vertical velocity, we figured out was 1.35. So you see this thing's going to go up until gravity makes it stop, and then it's going to start coming down. So it hits its top at 1.35. So that's the initial velocity, 9.8 t. So I can say, oh, how long did it take for him to reach the zenith of his dive? And so this is like a little linear equation you can solve. Let's see, how would I do that? T is equal to 1.35 divided by 9.81, and get T is approximately this. And the units that are involved here, that has to be seconds. Okay, so it doesn't, the guy's actually, in the water, or at least he's at the top of his thing very quickly. But the time up is the same thing as the time down. So I have to multiply this number by 2, and that's approximately, let's see, 0.28. If I multiply that by 2, and so that means that's the time up and the time down. So that is how long he is going horizontally at a speed of 2.9. So I take this is distance equals rate times time. And so this is 0.28 times 2.9. And this is approximately 0.8 meters is how far he lands from the end of the pier. Okay, I'm going to count to 5, Mississippi. I say Mississippi in my head just to see if people have questions, and you can shout out questions, or I guess I'm going to stop sharing here for a while. And let's see. Okay, so I stopped sharing. I'm going back here and I'm counting to 5. You can go off mic if you want to ask a question, or you can let's see, I suppose you could say a comment if you wanted to. Okay, so we have finished our review, and that is good. Okay. So now I'm going to go back and I will share some things, and we're really going to start talking about calculus then. All right, so here we go. Now, and Alex, just if I'm talking about something that isn't here, you tell me. But I think I'm getting a little bit more in the groove on this. So calculus is the study of limits, and so I will ask you limit questions, and I will ask you limit questions just that they're just limit questions. But then we will be studying 2 very special limits. One of them is called the derivative, and another one is called the integral. And much of our entire term is going to be spent studying these 3 things. Now, I did post a video just this morning. And by the way, please understand, I'm not trying to be rude, but some of you might say, well, damn it, Jim, you just posted that right before class started. Well, I'm juggling a lot of balls and things like that, just like you all are juggling a lot of balls, and we're dealing with crap and things like that. So I post it when I get a chance to post it. And sometimes I just say, well, no, damn it, I'm going to bed, and things like that. So anyway, I posted it there. I realize some of you haven't seen it, but also I'm going to work very hard. In fact, I thought a great deal about this. This is going to be so much simpler once we're back face to face, because I just go in and I'll just do things with you, and that's kind of it. Now I'm thinking about, oh, gee, I should make a video so that, the students are getting all the material they need, but then I have to, dance with the students online in Blackboard Ultra. And this really is, I think, very complimentary. The things that I do in the video, I am holding you responsible for. So do watch it. I realize some of you haven't had a chance to watch it yet. Go watch it. I actually think it is good. I work pretty hard on making good videos. So we got that, but this lecture is totally complimentary, and I will make a copy of this one also. So anyway, we're going to begin talking about limits, okay? And so we're going to begin talking about limits, and I am going to talk about, and I'm going to call this the hypothetical frog. Now, there is a point to this, and Alex, I really am not picking on you, but just so and if we were in a classroom, I just would be calling on people and asking them to say stuff, and nobody's grade is based on this or anything else. But Alex, I'm just going to talk to you if that's okay, because I don't want people to, feel embarrassed or to say, I had to let my dog out. So Alex, I will ask you questions.
Yeah.
And just bounce off and on. And I'm not recording whether you get these right or not. I'm just trying to have some interaction. Okay.
You got it.
All right. Good, Alex. So I'm going to stop sharing this. And now, Alex, I'm going to be going and I'm going to be sharing a whiteboard. And this is where we will be looking at the hypothetical frog. Okay, so Alex, you should see a whiteboard. Is that true?
That I do.
Okay, so here is the story of the hypothetical frog. And that's actually a very crappy picture. I can do better than that. So I'm going to erase that. Actually, I know a better way to erase that too. Okay, so this is the story of the hypothetical frog. And so let's see. Okay, and consider, Alex, that, and everybody else too, but in particular, Alex, that this is a table. And in fact, if we were lecturing in the classroom, I would use the table in front of the classroom to do this, okay? Now, Alex, we're talking about a hypothetical frog, okay? And Alex, you just give me, your answers. I am going to say I don't care if they're right or wrong. I think they're probably going to be right, but let's just talk about this. So anyway, we have a hypothetical frog that is starting here. And I am going to tell you about the frog's journey. Now, he is a mighty frog, and he strives to get to the edge of the table. So with all of his energy, he jumps, and he jumps about half the distance to the end of the table. So that was his first mighty jump. And so if you were talking about this being the table being L in length, this would be L/2. Okay, that's how far he jumped on this first jump. Now, although he's a mighty frog, that drained him a bit, and he can't jump L/2 again. In fact, he only has half as much energy as he has at the beginning, and so this hypothetical frog then is going to jump again, but this time he jumps halfway to the end again. Now, he had only half the strength that he had before, and so now this is another L/4 that he has jumped. Okay, and then he is a determined frog, and so he is going to jump again, but again he's burned a lot of energy here, so he can only jump half the way to the edge of the table again. And this, of course, this part of the jump, excuse me, would be L/8, I guess. Okay, and so on and so forth. Now, I am going to now do something that we all do a lot in this course, and I will say ... which means this frog keeps jumping, Alex, okay? Now, Alex, I'm going to ask you a question, and
Yeah.
I'll ask you a series of questions, but does the frog ever get to the end of the table?
At this rate, I'm gonna go with no. No, he does not.
And by the way, Alex, that is a good answer because he never does. Because if Alex had said, yeah, he does get to the end of the table, I would have challenged Alex and said, hey, how many jumps did it take him to get there? And the answer is he never really gets there. Now, and then I'm going to ask, actually, Alex, this is a rhetorical question. I'm not asking you to answer this one. Do we care? And the answer is yes, but it really depends. It's a little bit like Einstein's theory of relativity. It depends on who you are. Frogs eat flies, okay? And suppose that there was, and maybe you don't know a lot about frogs, you don't have to know a lot about frogs, but frogs have very long tongues, okay? So what happens is this frog, I hope you can see me wiggling my cursor, but this frog is getting closer and closer to the edge of the table, and eventually, even if there was a fly flying right above the edge of the table, the frog would get close enough to grab the food. So the frog would be happy at least as far as his nourishment goes, never really getting to the edge of the table. So the frog would be happy getting very close to the edge of the table. So the answer would be, well, the frog would be happy, at least as far as nourishment goes, to catch that frog, excuse me, to catch that fly, to get close to the edge of the table. So that is good. Okay, but now I'm going to put a different scenario. Suppose, Alex, and Alex, I am going to ask you to respond to this in just a moment. Suppose, Alex, that you were this is so much better in class because I can just call on different people. And I don't know, I mean, some people have left, some people are taking their dogs out, some people are doing homework for another class, who knows what. But when we're in class, we don't have that problem. Anyway, Alex, suppose that you were a frog catcher and you had designed an ingenious device that would taser the frog the instant he crossed the threshold of the edge of the table. Now, your taser is not going to zap him if his tongue flits across there. It has to be his feet have to go across the bottom for you to tase him. Now, would you end up being a frustrated frog hunter or a happy frog hunter in this case?
I'm not big on tasing frogs, but if I was, I think I'd be pretty unhappy.
Yeah, you can't catch the and I suppose I should do something less violent, but anyway, yeah, you're unhappy because he never got there. So you see, sometimes you care, sometimes you don't care. But there was nothing happening, and this does have bearing on limits. There was nothing happening at the edge of the table. But you see, the edge of table is something important because that's where the frog is getting very close to. And we're going to call that, and the edge of the table in this is, I guess I will write that down. So in this story, the edge of the table, the way Blackboard works is you can't see it till I'm finished writing. The edge of the table is the limit of the hypothetical frog's journey. Okay, I'm going to pause for a count of 5 if anybody wants to ask any questions about the hypothetical frog. Okay, I hit 5, so that is good. I am going to stop sharing that. I'm going to go back to sharing my applications screen. And let's see, we're going back to the PowerPoint show. Okay, now we're going to talk about a thing that is called Zeno's paradox of the tortoise and Achilles. Okay, and this is also about limits, and I'm going to ask you to pay attention to this because this is what I'm going to be asking you. Wait, I told you guys we were going to take a break, didn't I? I promised that. Okay, and I am going to ask Alex because I know he was there. I did promise you guys we would take breaks, didn't I?
Yeah, I think that might be.
Okay, we're taking a break right now. This is 10:20. We're going to resume at 10:30. Okay, so we'll resume with this. You guys can go to the bathroom, let your dogs out, or whatever. All right, 10:30. We'll resume.
Awesome. Thanks, Professor.
And you probably know this, but he would, and especially physically, I mean, he's like 6'8" or something. He's enormous. So now I'm in a little bit of trouble with this though, because this
Why?
actually is this, this is my daughter's jacket.
Oh.
But I couldn't find my jacket at home, and she wasn't wearing this. I mean, you know, so
Oh,
I
hey.
just took it. Now,
Free game
just if you knew my daughter, you would know she would resent this a little bit.
that you've taken it.
Yeah, that I mean, even though I'm putting it right back where it was,
Yeah.
yeah. But anyway,
That's wow. That's what it,
that was
did
a
it
gift.
come from Purdue? Like at a Purdue store.
I
Purdue?
don't know. I don't know how it's branded, but anyway, my son who went to Purdue bought this for her. So
I was going to say she
and
didn't go
and
to
they
Purdue,
and
right?
they want to send their kids to Purdue, and they're true Purdue people.
Your daughter does.
No, my
Your
son and his wife, they met at Purdue, and
Oh, okay.
they're Purdue people,
Okay.
really Purdue people.
So, does your daughter appreciate this, or is she?
Well,
she's
she
not a
appreciated.
Boilermaker,
No,
so.
she appreciated. She has a new jacket that she's wearing now,
Mhm.
and so I think
Your
I'm going
son should have really just given this to you. Why didn't he give this to you?
Well, no, it was a gift. It was like Christmas or
I
something along the way. So, but
but
yeah. Anyway,
clearly,
I was
you
showing you
probably
my.
would have appreciated it more than your daughter.
Yeah, I mean, she does wear it from time to time, but like if they're playing in a big game or
Yeah.
something, she might wear it. But yeah, I would have appreciated it more just because I'm.
Yeah.
My blood used to be
Black
black
and
and gold.
gold.
It was, yeah. So anyway,
What do you mean used to be?
still is, still is.
Come on, you never do that.
Thanks for coming and looking.
Oh, thanks for sharing it.
Okay, Alex, can you see a slide? And Verizon said it is 10:30. So can you see the slide?
Yes, the Zeno's paradox of the tortoise and Achilles.
Okay, now I'm going to read this, and normally in a classroom, I'd maybe have you guys read it just because, I can do that and things, but I'm reading it. Now, you might be saying, I'm not going to pay any attention to this. Pay attention to this because LSA 2 deals with this problem. Okay, so Zeno of Elea is credited with creating several paradoxes, and the best is the paradox of the tortoise and Achilles. Now, Achilles was a great Greek hero. For the purposes of this discussion, just think he is a great athlete. And turtles are like turtles, or tortoises are like big turtles, I guess. And so, anyway, the story goes something like this. The tortoise challenged Achilles, the great athlete, to a race, claiming he would win as long as Achilles gave him a small head start. Achilles laughed at this, for of course he was a mighty warrior and swift of foot, whereas the tortoise was slow and heavy. How big of a head start do you need? He asked the tortoise with a smile. 10 meters, the latter replied. By the way, hold on to that because in the problem I ask you about, 10 meters is the head start. So remember that. The story goes on. Achilles laughed louder than ever. You will surely lose, my friend, in that case, but let us race if you wish. On the contrary, said the tortoise, I will win, and I will prove it to you by a simple argument. Now, I am going to tell you that back in 450 BCE, before Common Era, and we used to call that BC before Christ, what happens is that the mathematicians really didn't have a good answer for Zeno's paradox. But anyway, so the story goes on with the next slide. Go on then, Achilles replied, but with less confidence than he felt before. He knew he was the superior athlete, but he also knew that the tortoise had sharper wits, and he had lost many a bewildering argument with him before this. Suppose, began the tortoise, that you give me a 10-meter head start. Would you be able to cover that 10 minutes between us very quickly? Very quickly, Achilles affirmed. And in that time, how far should I have gone, do you think? Perhaps a meter, no more, said Achilles after a thought. By the way, I'm pausing here for a side comment. So if the turtle went a meter in the same time that Achilles went 10, I'm being consistent with that in the numbers I give you later in the LSA. So I'm being consistent with the story. Okay, so the story, back to the story. Very well, replied the tortoise. So now there's a meter between us. You see the tortoise had moved to, well, you can figure that out. So now there's a meter between us, and would you catch up that distance very quickly? Very quickly indeed. That's Achilles talking there. And yet, in that time, I should have gone a little farther, so that you now must catch up that distance again. Yes, said Achilles slowly. And while you're doing so, I will go on a little further, and so that you must catch up that new distance. The tortoise continued smoothly. Achilles said nothing. And so you see, in each moment, you must be catching up the distance between us, and yet I, at the same time, will be adding a new distance, however small, for you to catch up again. Indeed, it must be so, said Achilles weakly. And so you can never catch up, the tortoise concluded sympathetically. You're right, as always, said Achilles, and conceded the race. You see, Achilles conceded without running the race. Okay. But you really, if you had a couple of more numbers, high school algebra, this is a high school algebra problem. Now we do need two more numbers. And so one number, and some of the numbers were in the story already, but suppose that Achilles runs 10 meters per second. Now, by the way, 10 meters a second is not being an Olympic runner, but that's actually very fast. Running the 100 meters in 10 seconds is fast. It's not it's not an Olympic record, but it's really quite good. And back in the days, they had bad shoes. So, Achilles was quite an athlete in my story. And to be consistent with the story, I'm going to suppose that the tortoise can run a constant 1 meter per second. So, but this is a high school algebra problem. Then how long does it take for Achilles to catch up to the turtle? So I'm going to stop sharing this, and I am going to go to, so Alex, we're looking at the whiteboard again. Is that true?
Yeah, looks good to me.
Okay, I'm going to try a power erase. Linda showed me how to power erase this. Yeah, that worked, good. Okay, so now I'm doing this the way you would do in high school algebra. Okay, and again, if I'm typing or something, it won't show until I'm done. But okay, so here we go. Then, so I'm doing this like high school algebra. So I'm going to say let T represent time until A catches up with T. And we know distance equals rate times time. Okay, and now you should be able to see what I was just saying. It should be showing up there. And again, Alex, if I'm not consistent with if I'm talking about something that you're not seeing, let me know, but I think we're good. Okay, so we know that. And the event, okay, and so T is when the distance A goes is equal to, actually, I'm going to say that the distance that A is from the starting line is equal to the distance capital T, standing for turtle or tortoise, I guess, is from the starting line. Starting line.
Are you drawing
Okay.
on the whiteboard right now? Oh,
No,
you're
I'll explain that again. The way Blackboard works, or the way this damn whiteboard works, if I'm typing a text box so you can read it, but I have to be finished with the text box and click offside the text box. So there will be a
my bad.
natural delay, that at least as long as I have to be doing this, like a Blackboardy thing, there will be an inherent delay that will happen. But now you'll see this, and again, and Alex will intercede on everyone. And by the way, your question was fine. I appreciated your question. But just, I mean, I'm sort of charging Alex today, and Alex, unfortunately, there's no extra credit for this except my undying appreciation. But if I'm talking about something that's really not here, why, say, hey, Jim, you're on the wrong page or something. Okay, so now I am though now, and I'm not sure who that was, so I'm not going to call him by name, but whoever was asking that question, I'm going to draw a picture. Ah, crap. Of course, I drew a bad picture. Eraser. I just want to erase part of this business. Okay, so I'm drawing the racetrack now, and the racetrack looks like this, kind of. But you see, here's the deal. The turtle got a head start. So you see, Achilles is starting back here. So Achilles starts here. This is the starting line. It's back there where you can see Achilles, but the turtle actually is starting here. Not turtle, but tortoise. Okay, but that's where the turtle is. But you might remember that this was 10 meters in this story, and so we'll just stay. And this is 10 meters. Okay, so that's what's going on. Okay, so this is the dynamic, but you see Achilles will catch up with the turtle whenever the distance that they are from this line is the same. Well, you see, this isn't very hard from an algebra point of view, and I am going to, and this will look like a 2-year-old writing, but I can't help that. Okay, so the distance that Achilles goes, it was 10 meters a second. Wait, maybe I'm going to do that better than that. Hold on. Okay, so I'm making an equation now. Okay, so when I set up that equation that I was talking about, if I talk about Achilles, that is 10 times t, that is equal to, now, um, what happens with the tortoise is distance equals rate times time, but this tortoise started at the 10-meter mark to begin with. So this is 10 plus, and then it is 1 times t. Okay, and now you should be able to see that equation that we solve. Well, that's a pretty easy equation to solve. What you can do is subtract t from both sides, and that'll say 9t is equal to 10. So the answer to this is that t is equal to 10 over 9. So you see, it's just a little bit over a second when Achilles catches the turtle, and this would be seconds, when Achilles catches the turtle or the tortoise in high school algebra. Okay, so you see, and mathematicians were pretty smart, so so how come Zeno was baffling them and what's going on? And this actually does have to do with that. Okay, I'm going to pause here just for a count of, I don't know, I'm going to say 5 to find out if people are, if anybody has any questions about this high school algebra thing that I did. So I'm pausing for questions. Okay, I hit 5, so that's good. You can always ask questions, but I'm thinking no one had any questions about that. That's good. So now, and I probably don't have to do this, but I think what I'm going to do is I'm going to snip this and paste this onto one of those PowerPoint slides. All right, so there's the high school algebra that we did. And now I'm going to stop sharing. I'm going to go back to, didn't want to do that. Okay. I don't want to send the snip. I just want to, this is all good. Okay, so now I'm going back to my application screen and I'm going to be sharing a PowerPoint slide in a moment, Alex. Okay, and then I'm adding a slide here. And Alex, what you should see is a PowerPoint slide that has the high school algebra on it. And I'm going to just tell me if you don't see it, but if you see it, we can just be quiet. Okay, so there I put high school algebra there. But now this makes, I'm actually ready for low stakes assessment 2. And so low stakes assessment 2, this is what it says. So low stakes assessment 2 is due 2/14. That is Valentine's Day for what it's worth. If not before, because I'll let you upload it before. I have to go create the place for you to upload it, and I've got things I'm doing after this lecture, so I don't know how that'll all work, but it will be there anyway. But this is what I'm asking you to do. Is I'm asking you to, first of all, resolve Zeno's paradox with our high school algebra solution. You have to think about this because resolving means you have to show that, yeah, they're really the same thing and why Zeno was wrong. And you might think, oh, this is a trivial thing. Not necessarily, because mathematicians back in 450 BCE didn't have a good answer for Zeno. And fully address the questions associated with Thomson's lamp. You might say, well, what is Thomson's lamp? Well, it's this. And it is related to that. So I'm reading again to you just because I kind of have to read it there, but you have it there. You can take notes and so on and so forth. Okay, Thomson's lamp. Consider a lamp with a switch. So if you hit the switch once, it turns it on. If you hit it again, it turns it off. So let us imagine there is a being with supernatural powers. I don't want to talk religion with you, but I will tell you that there's a whole bunch of things in the world that we don't understand, like quantum mechanics. And so there are supernatural power things. But okay, so there is a being with supernatural powers who likes to play with this lamp as follows. First, he, and I'm not trying to be sexist, that's just where I tore this out of it, called it he. It could be she, I don't care. In fact, most of the time when I think about God, God isn't a he or a she, but I often think about God as being a she, actually. First, this supernatural person turns it on. At the end of 1 minute, they turn it off. At the end of a half minute, they turn it on. And at the end of a quarter minute, they turn it off. In 1/8 minute, he turned it on again, and so on and so forth. Kind of reminds you a little bit, although a different physical context, with the hypothetical frog that we studied before. It should, anyway. Again, it's getting you thinking about limits. And so hitting the switch each time after waiting exactly 1/2 the time we waited before hitting it, applying the above discussion, it's easy to see that all these infinitely many time intervals add up to 2 minutes. You might even have to think about that. Why does it add up to 2 minutes? But anyway, at the end of 2 minutes, the question is the lamp on or off? And there's another question here. The lamp started being off. Would you have made any difference if it had started being on? So you see, this is the LSA 2. Okay, and I will be posting this and stuff like that, and I will be, stopping the video and things like that. I do always know what time it is. It's almost 10:47. I'm not going to waste the time though. I'm going to go through it. I'm going to poll people. This is not taking attendance, so I'm stopping sharing here, and I'm going back to this thing. Yeah, somebody made a comment there that was actually interesting. Oh, okay. Yeah, I could talk a long time about that, but that's not math. So, yeah, and I mean, those are very deep questions. Those are deeper than the math we'll be studying. I am going to poll people though, so I'm going back to the attendees. I'm just going to call your name. You can give me and by the way, you can give me a thumbs up, or I'm really trying to see, do you have any questions? Are you good with things? Alex, I'm starting with you.
I am all good. I don't know if that's what I was supposed to do, but yeah.
That's all you need to do. Okay. I also have Ternio. How are you?
I'm fine, and I don't have questions.
Good. That's fine. Cecilia,
I'm here. Also, I have a question.
go ahead with your question.
Okay, so inside the tech the online textbook shop, they show 3 options to buy for calculus. What's the option I'm supposed to click on?
I'm not going to make you use my math lab, and there's decisions that you have to make if you want to buy, a whole book or things like that. And I'm happy to talk with you specifically in office hours, but it really depends on what you're doing. And getting by as cheaply as possible is okay.
Okay. Also,
So
yes, Timur. Sorry if I pronounced that name wrong. It is from Brooklyn Nine-Nine.
okay, so
Millinetti's the
that's
best character. Don't at me.
okay. So that was good, and thank you. Okay, Cecilia, and we got a question answered there too. Hare Patel, please. I might go a little bit over 10:50, but I want to hear from each of you. This will be quick. Hare Patel.
Yes, I don't have any questions.
All right, excellent. Jeffrey Weinholtz.
I also do not have any questions.
Thank you. Okay, we'll keep going, and we'll go to Joseph Vaselli.
I'm all good.
Great, thank you. Kang Lee. He is good. Okay, Mark Zayden.
Yeah, I have one question. Will we have
Go
like
ahead.
supplemental videos when we're back in class, or just for this 2-week period?
I don't know. I haven't decided yet.
Okay.
And so I don't know. I mean, if there are other videos, I'll say, hey, I made a video for you to watch or something. Okay. I
Okay.
don't know how this will work. I hope to hell we're back in class, actually, but we'll
Yeah.
see. Matthew Sanders. He is okay. Matthew Sanders is maybe he's letting his dog out or having technical difficulties. I don't know. I hope he is well. Okay, Steve Terikov.
Oh yeah, I'm all good.
Excellent. Timur, how are you?
I'm good.
Excellent. Thank you. And last but not least, Tony Beliza. Hi, no questions. Okay, I'm hoping that means you're good. All right, so very good. We're finished for the day. And I'll see you. Oh, I guess we're finished for, no, we meet on Friday. So I'll see you on Friday. And I'm stopping the recording now.